Okay, continuing on with this problem. So again, we got to the point where we're really just doing some algebra. We FOILed all that out. That gave me that. Then I distributed that minus sign, and then 16 minus 1, 15. Then it's legal to split up summations by subtraction, so I split this up into 3 summations. Because I have a formula for when I have a constant. I have a formula for k, and I have a formula for k squared. So that's why I split it up into 3 separate summations, because I have formulas for constants, I have formulas for k, I have a formula for k squared. Continuing on. Again, the variable of the summation is k. We aren't going to worry about the limit until absolutely the end. The variable of the summation is k. So in this summation here, the 4 over n, that's just a multiplied constant. It can factor out. Same thing on the next one here. In that summation, the 4 over n squared. Since the variable for the summation is k, the 4 over n squared is just a multiplied constant as far as the summation is concerned, and it can factor out. So that's what we did on the next one. We just factor out the 4 over n and the 4 over n squared. Because we're concentrating on the summation, the variable of the summation is k. Now we're going to use our formulas. We had a formula for k. K equal 1 to n was given by that formula. The formula for a constant, k equal 1 to n, was c sub n. And k equal 1 to n of k squared was given by that formula. So we're just going to use each one of those formulas, really replacing the whole summation k equal 1 to n, and k equal 1 to n, k equal 1 to n of k, and k equal 1 to n of k squared. We're just going to replace those by their formulas. So just repeated it again so we have it all kind of together. So there's where we're at. Summation from k equal 1 to n. That's this formula, Cn, where c in this case is 15. So we have 15n. Then we see the minus 4 over n, and then I just replace that summation with its formula. Its formula is right there. N times the quantity n plus 1, all divided by 2. Replace it with the formula, and same thing on the end. The 4 over n squared, that's just a coefficient, stays there. Then replace the whole summation with its formula. N times the quantity n plus 1 times 2n plus 1, all divided by 6. And so there we have done all the summations. The summations are gone because we were able to replace them with formula that we had. Now back to just algebra. Simplify, simplify, simplify. So on this first one, from here to here, the 4 and the 2 canceled, leaving 2. And the n's just canceled out entirely, leaving me 2 times the quantity n plus 1. On the next one, the 4 and the 6, I can divide those by 2, getting 2 and 3. The n and the n squared canceled, leaving an n. So in the numerator, I have a 2, an n plus 1, a 2n plus 1, and in the denominator, a 3n. So all we did was some basic simplification there. Keep simplifying. So on the next one, all I did was distribute. The negative 2. That's all I did there, and then I FOILed all that out, and you can just trust me that I multiplied all that out, got that. Hopefully I didn't make a mistake. But that's all I did there, is I just multiplied all this out. So I get to here. Then I just combined some like terms, 15n minus 2n, 13n. Didn't do anything else out. Next, distribute the 2 over n factor. So all I did was distribute this guy. 2 over n times 13 over n. The n's cancel. 2 times 13, 26. 2 over n times 2, 4 over n. And lastly, two over n times all that. So I distributed the 2 through the numerator to get 8n squared plus 12n plus 4. Just distribute the 2 through the entire numerator. And then on the denominator, 3n times n, 3n squared. Now, finally, I'm going to look at the limit. Finally, some calculus. Really, up to this point, there hasn't been any calculus. Now we're going to do some limits. So we know that we can split up limits by subtraction. So that's all I did there, split it up into 3 limits, because I know each one of those. The limit of a constant, limit as n goes to infinity of 26, is 26. This should not be, this is in the wrong place. That right there is supposed to be over here. Who knows how that got clear over there? Try to fix that someday. So the limit as n goes to infinity of 26 is 26. The limit as n goes to infinity of 4 over n. Well, you got basically 4 divided by something going off to infinity. That's going to be 0. And then the limit as n goes to infinity of n squared, 8n squared plus 12n plus 4 over 3n squared. So something we learned weeks ago. My degrees are equal. So this is the limit at infinity of a rational function. We had a shortcut for that. Limit at infinity of a rational function. You could just look at the degrees. These are both degree 2. The limit of, so then you could just pull off those coefficients. So my limit is going to be 8/3. So 26 minus 0 minus 8/3, 23 and 1/3. And there's my exact area. Previously, we had calculated that the area had to be between 21.25 and 25.25. We now know that the area is exactly 23 and 1/3. And the way we did that was to add up the areas of infinitely many rectangles. And when we did that, so that you had infinitely many rectangles, so those rectangles kept getting smaller and smaller and smaller till they're really line segments. And so the line segments fit perfectly. There was no underestimate or overestimate. Those line segments fit perfectly. And so what we really ended up doing, go back and find my picture. We ended up filling this region with line segments. And those line segments, when we added up infinitely many one-dimensional line segments with just the length or the height of each one of those line segments, that gave us 2-dimensional area. Okay, so getting ready for the next section. So we're just going to have some terminology here that'll carry over to the next section. I'm not going to do any more problems in this section, so some terminology. So in the above problem, we used rectangles of equal width using right-hand endpoints with a region above the x-axis. This was a special case called a Riemann sum. And a Riemann sum, again, is just that idea of adding up infinitely many rectangles. That's all a Riemann sum really is. However, in general, Riemann sums are not so specific. We are very specific in this previous problem. Above the x-axis, equal width rectangles, right-hand endpoints. We are very specific. And so that was just a specific example of a Riemann sum. But in general, they don't have to be that specific. We may use any unbounded region above and or below the x-axis. We may use different rectangles of different widths. We may use any point within each interval. To demonstrate with a Riemann sum, let's start with an arbitrary function on the interval a to b, and we will subdivide the interval ab into subintervals, choosing n minus 1 points, blah. And so all we said there, all that part there is that I just took my interval and I plunked down a series of points between a and b. Maybe they're close together, maybe they're far apart. I just plunked down a bunch of points between a and b. is such that A is x naught less than x1 less than x2 less than x3, blah, 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 blah. These points here are called a partition. So instead of saying I'm drawing rectangles, so what we did before, all our points represented bases of rectangles. The only difference here is, okay, we're not going to call these bases of rectangles, we're going to call them a partition. A partition is just where you've subdivided an interval into subintervals. That's all a partition is. And these intervals don't have to be of equal width. Notice here x2 to x3 looks bigger than x1 to x2. The set of points is called a partition. The into a set of subintervals, blah, blah, blah. And then we call the width of these subintervals delta x sub k. Because not all the widths have to be the same, so instead of saying delta x, we're going to say delta x sub k. But that still just means a width of an interval. Then we form a bunch of rectangles where the heights of those rectangles don't have to be in a common place. So here it's on the left, here the height is on the left, here it appears to be the midpoint, here it's on the left, here it's a little bit past the midpoint, but the point is where the rectangle meets the curve doesn't have to be the same in each place. And notice we have some rectangles above the curve, some rectangles below the curve. And I have there, note the rectangles are not of equal width, nor do their heights meet in a standard location within the interval. Next, we form the product f of c sub k delta x sub k. Now notice f of c sub k each time is just the height, and you can't see me, but I put height in air quotes, because when it's below the x-axis, that's going to be a negative value, so maybe I shouldn't call it a height, but I don't know what else to call it, so I'll call it a height. We form the product f of c sub k delta x sub k. Really, height times width. So still area, but it's just that some of them are below the x-axis, so it'll be a quote-unquote negative area. In this case, when the corresponding rectangle is below the x-axis, this product is negative. If the corresponding rectangle is above the x-axis, this product is positive. Finally, we form the sum s sub p equals the summation from k equal 1 of f of c sub k delta x sub k, which is the Riemann sum for f on the interval AB with partition B. So there's an official Riemann sum. But all you really need to comprehend here is it was just adding up areas of rectangles. Rectangles that might be fat, rectangles that might be thin, maybe the rectangle's above the x-axis, maybe the rectangle's below the x-axis, maybe the rectangle meets on the left-hand side, maybe it meets in the middle, but it's just adding up areas of rectangles. And again, areas in air quotes, because if it's below the x-axis, that value could be negative, or if it's below the x-axis, the value will be negative. So Riemann sums can be positive or negative, depending on the specific Riemann sum. Then lastly, a function can have infinitely many Riemann sums depending on the partition chosen and the value of c sub k chosen. The values of Riemann sums may be positive, negative, 0, depending on the function in the interval. But all you really need to remember at this junction is a Riemann sum is the idea of adding up areas of rectangles, where I put areas in air quotes, if you could see me, air quotes, because if it's below the x-axis, that product would be negative. And that's the end of this section.